In item number 2, we are looking at the likelihood that in this system we can go from the far left at state 0 to the final at state Z. The paths are such that we've got two major paths in sequence, but within each one of those major components there's a parallel set. We just have to be able to find one way to get through here successfully. That's what this model is setting up. Inside of each of the boxes of events A, B, C, D, and E are the probabilities that we can get through that successfully. So let's zoom in and see if we can't figure out a nice simple way to do this. Right? So one thing that I would say is right away let's look at, to get through this one branch, we can replace that with a single event that's going to have, oh hey, when we do this, that's the probability of A and C. That's equal to the probability of A times probability C. That's our 0.95 times 0.98, and that will equal 931. Right, so we can replace that with a single probability. Right, and then if we look at this entire system on that side, let's call that F, then the probability that we are successful going through F is going to be the probability of that AC combination or B, and that's given to us by probability of AC plus probability of B minus the probability of the intersection, and since they're independent, those intersection events are just a straight multiplication of the marginals, and so we'll have that that's equal to 0.931 plus 0.99 minus the product of those two, and that product would be 0.99931. Very high chance that we will successfully get through that. And then likewise we have the same kind of setup here on this last one. Probability of G is equal to the probability of D or E being successful. Yeah, so that's probability of D plus probability of E, the marginals minus the intersection events, so product of the individual marginals. And there we'll have 0.99 plus 0.92 minus the product of those two, and that is 0.9992. And then finally, now we just have an intersection event. That the probability of going from state O to state Z is just the probability of success of F and G, because now we have two systems that are in sequence with each other. That, because of independence, is just that simple product of those two. And so that's our 0.99931 times 0.9992, and we end up with a final answer that is 0.99851. In other words, very high probability of success, at least for, well, it seems like it, right? Depends on the consequence of that very small probability of failure, whether this is considered to be high or small.